We're in section 3-7, and this has to do with electricity. So if I have a voltage source, and that voltage source goes through some resistance R, and across some inductor L, and through some capacitor C, back to the voltage source, then I'm going to have some current flowing in the thing. By Ohm's law, we know the voltage across the resistor is IR, current times resistance. Not using Ohm's law, but using other things, we know that the voltage across the capacitor is Q over C. And we know the voltage across the inductor is going to be L di dt, where capital I is current, let's spell current, and little I is current, Q is charge, in coulombs, and C is farads. The capacitor is measured in farads. The inductor L is in Henry. So those are just we'll put brackets around these things to indicate that they're units of measurement. And R is resistance, which of course is futile, as we all know, from Star Trek. Yeah, resistance. We also know that the voltage of the sources, the summation of the voltage of the sources, has to equal the summation of the voltage drops. So as I go around my circuit, I start someplace and I go down, I go down, I go down, I go back up. And when I get back to where I started, the voltage has to be the same. Because if it isn't, then I'm going to have a great big fireball as charge builds up until it gets to a point where it just leaves the wire and flows out in space as a fireball. And that doesn't happen very often, so we don't have to worry about it too much. Okay, well in that case, the voltage, source voltage, has to equal IR, the voltage across the resistance, plus L di dt, the voltage across the inductor, plus Q over C, the voltage across the capacitor. Now, 1 coulomb per second is going to be 1 amp. So my charge is flowing in coulombs, and a whole coulomb in a second gives me an amp. And do we remember the charge of an electron? What's the charge of an electron? Well, I think I remember, but it's been a little while, like 2 or 3 seconds or so. But I do have a calculator that will tell me constants and will tell me the charge of electron. It's something times 10 to the minus 19th. And speed of light. Oh well, Guess I should have written it down before. Sorry about that. There, the less mass of electron, mass of proton. Charge on an electron, found it. Yes, that's right. Okay, charge on an electron, 1.6 times 10 to the 19 coulombs. So a coulomb is a pretty big amount of charge, but electron's an extremely small amount of charge, so that's the way that works. And we probably don't need to know that anyway. The other thing we need to know is that current is the change in charge per time. So that's why I did this up here. 1 coulomb per second's an amp. Well, your current, let's go back up to the top for just a minute. A big I current normally means a DC current. A small I current normally means an AC current, a current that's changing with time. Okay, so but Ohm's law is going to be the same whether or not I have AC or DC. It's going to be the same voltage drop. It's just going to be a time-dependent voltage drop if I have AC current. If I have a changing current, I say a fixed voltage drop if I have DC current. Okay, well, that being the case, that I is equal to dq dt, then the voltage across the source has to equal L. Well, see if I can get that more centered here. The voltage across the source has to be L dq, the second derivative of charge, dt, plus R dq dt, plus Q over C. So whenever I'm dealing with a circuit with an inductor, a capacitor, a resistor, and a voltage source, I'm dealing with a second order differential equation that I need to solve. So that's what that's all about. So now we're going to look at problem number 2. And problem number 2, given the same circuit as in problem 1, suppose that the switch is initially in the position 2, but it's thrown to position 1 at time 0, so that current at 0 is 0, voltage is 100 volts. Find IT and show that it goes to 4. Okay, gotcha. Alright, so number 2, we've got some current source and it is 100 volts, so basically it's a DC source, and you have a switch that's in position 2, comes all the way down, and there's position 1, got a resistor, 25 ohms, and we have an inductor, 5 Henry. Now 5 Henry is a pretty big inductor. A 50 millihenry inductor is about the diameter of a dime and about an inch high. So this guy's a pretty big thing. Okay, so that's the case. We know that the current at time 0 is going to be 0. We know that. And at time 0, I'm going to close the switch. Okay, so that being the case, voltage source, the E, is going to be I, R, plus L, di dt. Okay, so putting our numbers in, we have 100 is equal to 25i plus 5i prime. And it looks sort of like a differential equation. And we can simplify it because I can divide everything by 5. So I'm going to do that. I prime plus 5i is equal to, well, it doesn't look like an I. 5i is equal to 25. Yeah, it's equal to 20. It's even better. Okay, now to solve. I have a characteristic equation. R squared plus R squared. Who woke up today? R plus 5 is equal to 20. But we need the characteristic equation of the homogeneous guy. Okay, so R is equal to minus 5. So y sub c is c1 e to the minus 5t. Okay, and now we have to come up with a particular solution now that we have the homogeneous solution. So my particular solution A, the derivative of my particular solution, 0. I have 5 of those guys, one of these guys, and when I get done I want to have 20. So 5a is 20, clearly implying that a is equal to 4. So my final answer, I of t, is going to be equal to, well, it's not the final answer yet, c1, not yet, because I still have an initial condition to apply. c1 e to the minus 5t plus 4. Okay, now I'm going to apply my initial condition, and my initial condition says I at 0 is equal to 0, which would imply that c1 had better be equal to minus 4. Otherwise that wouldn't be the case. So now I've got a part of the answer, it is equal to minus 4e to the minus 5t plus 4. So that is the final answer of what the current is. But then it wants us to continue to what is the limit of that current as t approaches infinity. So what's the limit of the current as t approaches infinity? And we look at that and we say, well, look at this. This guy here goes to 0 pretty quick, and the answer is 4. So 4 amps, after the switch is closed for a goodly part of time, like maybe a couple seconds, from there on, the capacitor, the inductor is fully charged, and current stays at 4 amps. Okay, let's look at number 4. Number 4. In a circuit, figure 377, with the switch in position 1, suppose that inductance is 2, resistance is 4, we have a voltage source, and the current at time 0 is 0. Find the maximum current in the circuit as t is greater than 0. Okay, so all right. Now in this, you'd say, well, isn't that the same problem as we had before? And the answer is no, because now our source is not a DC source. So my current, my voltage is 100 e to the minus 10t. Okay, but it's a source that's going, it's not, at least it's not a sine wave source. Okay, so we can have that. We have a position 1 and a position 2. Okay. At the beginning of the problem, it wasn't in position 1, and it was obvious it's going there at time 0. So, all right, maybe hard to say. Okay, so I've got a resistor that's 40, and I have an inductor that's 2 Henry. 2 Henry. Okay. And I have a problem that says 100 e to the minus 10t is equal to 40I plus 2 di dt. And I have an initial condition. What are they? I at 0 is 0. Okay, so that's what's happening. All right, well, I've got a differential equation. So 2I prime plus 40I equals 100 e to the minus 10t. Divided by 2, I prime plus 20I is equal to 50t, e to the minus 10t. Alright, so at time 0, when that, what happens is that this is a 1, and I have 50 volts across it, and then as I go, as time, the voltage source goes down. Okay, so what are we going to do with this? We have an initial condition. Oh, no, we don't. We have a characteristic equation. Okay, so I got a characteristic equation. R plus 20 equals 0 for the homogeneous equation. I have R is equal to minus 20, and I have I of t is equal to, and this is the homogeneous solution, C1 e to the minus 20t. And I want to find, gotta solve for C1. So I is equal to A. E to the minus, how did I get 20t? Who did that? 10t. 10t. And I prime is equal to minus 10a e to the minus 10t. And if I take 10, if I take 10 of these, and what? Okay. I'm not looking at the problem here. Let's see what it's 20, 20, 20, 10. Okay, that's fine. 10, that's fine. Okay, everything's good there. So I got 20 of these guys and one of those guys, and when I get done I need to have 0 because my initial condition says that I will have 0. Okay, so I got 20a e to the minus 10t. Well, I have 20 minus 10, so this is going to be a 10a. Okay, so I got 10a e to the minus 10t. Okay, so I'm going to put that back in my original equation. Where did my original equation go? Okay, so I sub t is going to equal C1 e to the minus 10t plus 10. A has to be 0. A has to be 0? A has to be 5. A has to be, this isn't 0. What is that? That's 50 e to the minus 10t. This has to be 50 e to the minus 10t. So A has to be 5. Alright, so I got 5 e to the minus 10t. Now, I at 0 has to be 0. So C sort of implies C1 has to be minus 5. Alright, so final answer for my current, I of t is equal to minus 5 e to the minus 10t plus 5 e to the minus 10t. And guess what that is? That is 0. So there is no current. The max current is 0. And yeah. So if we come back up to the problem, I'm in this position. It's already there. Everything's already charged. This guy's already down to 0. So the max current after time 0 is still going to be 0. I don't have any. Isn't that lovely? Now, is that really what we want? Let's see. 4. In the circuit, blah, 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 with the switch in position 1, suppose inductor Z, current Z, and current at time 0 is 0. Find the maximum current in the circuit for t greater than 0. Yep, 0. It's 0 now, it's going to be 0 later. It's not going anywhere. Oh well, sometimes differential equations are so much fun. Alright, one more and then we'll call it a day on this particular section. Number 8. We have some electrical source, we have some switch, we have a capacitor, we have a resistor. Okay, so E is going to be 100 e to the minus 5t. 100 e to the minus 5t. And I have a resistor of, is it 80? Resistor number 8. Okay, so I have a resistor 10 ohms, and I have a capacitor 0.02 farads, and my charge at time 0 is 0, and my voltage is in volts. Find Q of t, find I of t. What is the maximum charge on the capacitor for any time after t is equal to 0, greater than 0? And when does it occur? When does that maximum charge occur? Okay, so first of all we have to get that the voltage source has to be dq dt R plus Q over C. Okay, so we know that, and that's going to be 100 e to the minus 5t has to be 10 q prime plus 50q, because 1 over 0.02 right there, right? That's 50. Okay, so I've got a differential equation. I can divide everything by 10, so I will. 10 e to the minus 5t q prime plus 5q. I have a characteristic equation. R plus 5 is 0. And I know that q at times t for the homogeneous solution is going to be c1e to the minus 5t. Okay, well that seems reasonable. Well, I'm going to get a particular solution, q sub p, and it has to be a e to the minus 5t, and q particular solution prime minus 5a e to the minus 5t. And from the differential equation, I need one of them. I need 5 of these. And oh, yeah, we forgot something already. What did we forget? Well, the homogeneous solution has e to the minus 5t in it, and so does the particular solution. Therefore, we need a plus bx e to the minus 5t. We need a plus b e to the minus 5t, and we need a minus 5 bx e to the minus 5t. And so that's what we forgot. Well, we just remembered it. So 5 of the A guy minus 5, so that guy goes away. I have 5 of this guy, 5 of that guy, so they go away. So I'm going to have b e to the minus 5t, and what am I supposed to get? I'm supposed to get 10 e to the minus 5t, so b is clearly 5, also known as 10. B is 10. So now my q sub t becomes c1 e to the minus 5t plus 10t e to the minus 5t, and I have initial condition. What is it? Q at 0 is 0. Is that what it is? Hey, Q at 0 is 0. So from the initial condition, Q at 0 is 0, which is going to be C1. So C1 becomes 0 because this guy goes away. All right, so my final answer for my Q of t is 10t e to the minus 5t. All right. Now we want to know the current at time t. What is the current going to be at time t? Well, the current at times t is the derivative of the charge at times t. So that would be 10 e to the minus 5t minus 50 t e to the minus 5t. And do I have another? All right. So that's the end of part A of the problem. Part B of the problem wants to know what is the maximum charge on the capacitor for some time greater than t? Okay. So, current is going to be 0. The maximum charge of the capacitor is going to be when current is 0. As long as the current's flowing, the capacitor is continuing to charge. So when the current is 0, at that time we have the maximum charge. So current is 0 when? At 10 e to the minus 5t minus 50 t e to the minus 5t. Okay, so we're going to divide by e to the minus 5t. 0 is equal to 10 minus 50 t. T becomes 1/5 of a second. So at 1/5 of the second, my current will be maximum and stay there forever. My charge on the capacitor is maximum, will stay there forever until I do something about it to have it go away. So charge at 1/5 of the second on the capacitor, 10, 1/5, e to the minus 1/5. 1/5. And what is that equal to? Okay, so 2. 2, turning on my calculator, 2 times e to the minus 0.2. And I come up with 1.637 coulombs. Oh, and that would be wrong. Okay, well, let's do it again. You guys already told me it was wrong, so anyway. Because it's minus 5t, so minus 5 times 1/5 is going to be 0. It's going to be e to the minus 1 and not e to the minus whatever. 0.736 coulombs. And now we've solved both A and B of the problem. And that's all that we're going to do in section 3.7.